Welcome to a discussion about EonCoat. We will cover how and why it works and the billions of dollars we can bring to your bottom line. I start by asking folks if they recognize this picture. It is the Iron Pillar of Delhi, a 1600-year-old steel pillar, and you can still read the inscriptions. About 40 microns of corrosion in 1600 years. I start with this slide because I'm going to make some bold claims about what EonCoat can do, and I expect you to challenge me on those claims. But let's get past whether it is possible to stop corrosion permanently. It has already been done in India 2,000 years ago. Before we dig into the details, let's start with a bit of history. The technology you are about to see was pioneered by Argonne National Labs under contract for the U.S. Department of Defense for the purpose of shielding radioactive waste. They have one customer, the Savannah River Project. What they do with the cement is classified, but since it is common knowledge that the site is where the United States makes nuclear weapons, you can probably connect the dots. After reading about the technology in 2007, we purchased the rights to all uses of the technology except for nuclear waste. We funded further research which led to a plethora of intellectual property. Perhaps the most consequential is a cement that stops corrosion on carbon steel. In all likelihood, it is permanent. Let's talk about how it works. This is how we do it. First, we alloy the metal. Then a ceramic layer that protects from abrasion and continually leaches phosphate to repair any holes in the alloy layer. Finally, if all else fails, triggering the formation of a very old and rarely seen protection mechanism, the same one that protects the iron pillar. This is the fundamental chemistry of the reactions that form the alloy layer and the ceramic layer which leaches phosphate. This is a photo taken by a scanning electron microscope which shows how the metal is actually alloyed. This picture is the width of one blast profile from peak to peak, about 20 microns wide. If this were a polymer coating, the valley of this profile would be open because polymers stick to the peaks but don't reach down into the valleys. This causes water to roll around in those valleys if it ever penetrates the barrier. As you can see, EonCoat gets all the way into the valley and alloys the metal. This is a very high magnification of the actual alloy layer as it mates with the base metal. We damaged the layer a little in order to show you these photos. Notice that the alloy layer is only a few microns thick, but in the world of corrosion, that is plenty. The protective layer on stainless steel is measured in angstroms. 1 micron is 10,000 angstroms. Now for a little independent validation. Everyone in our industry agrees. The toughest real-world test is the NASA beachside conducted at Kennedy Space Center. All manufacturers' tests at NASA. You will never see a result published because everyone fails, but a score of 8 out of 10 here indicates you have one of the best coatings in the world. This is the brutal test protocol that NASA uses at the most corrosive site in North America to qualify coatings and materials for use on NASA's own launch facilities and other critical equipment. And here are the results NASA published in 2014. These slides were taken directly from NASA's published report. I'd be happy to send you a copy of the complete report. You can see the results. In case you are wondering, EonCoat is circled in green. The 11 best coating systems that NASA could find. All of them good, but a little company from Wilson, North Carolina delivered what none of the majors ever have. A perfect 10. And just for a bit more independent validation from someone you likely respect as the thought leader in the oil and gas sector, here are 2 separate presentations done by Chevron to explain their extensive testing and use of EonCoat technology. The first was done at Eurocore in 2018 about our CUI, Corrosion Under Insulation product. The second at NACE, or AMPP as it is now called, in 2023 about our weldable coating for the soil-facing side of tank bottoms. Both presentations are public, and I'm happy to send you the videos and complete documentation of each. Before moving on to some technical data, let me brag on my scientists for just a moment. In any industry, the most prestigious awards are the ones that come from your peers. In corrosion, that award comes from the National Association of Corrosion Engineers, and it is called the Innovation of the Year. The trophy from 2015 resides in our conference room. Now, if you will stay with me through 6 slides that I'll go through quickly, you will see what prompted me to spend a lot of money and years of our lives understanding and perfecting this technology. We will see what happens when the protective mechanism I've described fails. We started with the rusted panel you see on the left. No surface prep, just rinsed with water and coated the rusty steel. Then put it in a magnesium chloride salt fog chamber, an extremely aggressive corrosion test. Through the first 1,500 hours, the results looked pretty good. Even up to 2,500 hours, the panel looked quite good, but began to show some degradation underneath the ceramic at 2,800 hours. Then something really odd happened. The panel got better as we went to 4,000 hours. As we pass through 5,800 hours, the panel continues to get better and then worse. By the time we reach 7,500 hours, the panel is looking like we are about to see massive failure. We almost removed it. Thankfully, we did not, because it enabled us to discover the most significant lesson about corrosion control in 2,000 years. But then the panel begins to heal again. We were stunned. We had no explanation for this. Rusted steel doesn't get better. And at 12,000 hours, we were completely baffled. A year and a half in a brutal salt fog chamber, and the panel looks about like it did when it went in. The scientists needed to know why. You recall I started this presentation with the iron pillar of Delhi. You are about to see why. In 1971, the famous Japanese scientist Misawite predicted that iron could be protected indefinitely if a way to convert the crystalline layers of FeOOH, the lowest energy state of iron, to an amorphous layer could be found. He predicted that this was possible by catalyzing the reaction with one of three elements: copper, chromium, or phosphate. 30 years later, the famous Indian scientist Balasubramanian from the Indian Institute of Technology was given permission to test the iron pillar of Delhi. This was a huge deal because after 1,600 years of no rust, the pillar had become something of a religious artifact. What Balasubramanian discovered was exactly what Misawite had predicted so long ago. He named the layer Misawite in Misawa's honor. 10 years after Balasubramanian, in a lab in Wilson, North Carolina, my scientists tested that rusted panel I've been telling you about by removing the ceramic and using sophisticated tools to examine the spots which had healed. What they found was Misawite. The failure mechanism of EonCoat is the creation of Misawite. Once you get the amorphous form of FeOOH, the game is over. The layer will not flake off as crystalline FeOOH does, and it cannot corrode further because FeOOH is the lowest energy state of iron.